Hello friends, this is Vipin Kumar here. Welcome back to my YouTube channel Vipin Tech Tips, and in this video I'm going to discuss the solution of GATE 2015 for aerospace engineering, and in this video I'll be covering the problems from flight mechanics 1 and 2. So mostly I'll be completing this video in two parts because so many questions are there. So let's start now. So as you can see here, I have collected the questions from GATE Aerospace website, official website, and here, if you look at the questions, so question number 6, question number 7, 8, 9, 10, 17, 18, 20, 19, 20, 21 are for 1 marks, and 32, 30, 45, and 50 are for 2 marks each. So total 16 marks are there, and from these questions I have removed the questions which are from the dynamic stability and from the directional and rolling stability, so that I will be covering all the questions from related to these topics in a separate video. So here, even if you look at this total set, out of 20 marks, 16 marks are basically from the longitudinal static stability. Okay, one or two questions are from directional stability also. So let's start with this. So here is the question number 6. Consider the density and altitude at the base of an isothermal layer in a standard atmosphere to be P1 and H1 respectively. The density variation with altitude and that layer is governed by R, T and G naught. What will be the variation? So density variation with altitude. If you look at the answers, you will see that two answers look similar, this one and this one, which we know that one of the answer out of these two is going to be correct. Okay, so we can eliminate these two choices here, but before that we'll discuss what is isothermal layer and what is the different types of layers. Okay, so basically when we talk about the atmosphere, so there are some layers. Okay, so according to the variation in temperature, the behavior of these layers is categorized into gradient layer and the isothermal layer. So in gradient layer there is a temperature change with altitude, and that term is called dt by dh, also denoted by a, also denoted by lambda. Okay, and is called lapse rate. Okay, so rate of change of temperature with altitude. So here in this question, we talk about the second layer, which is the isothermal layer, and in isothermal layer, as the name suggests, temperature is constant. Okay, in this layer if I want to derive the expression for density variation, so I can make use of hydrostatic equation, which is given by this expression: dp is equal to minus rho g naught into dh. Okay, so dp is change in pressure, which is equal to minus density into g naught into change in altitude. Okay, so if I divide this equation, let's say this is equation 1, if I divide that equation by equation of state, so equation of state is p is equal to rho rt. Okay, where p is the pressure, rho is the density, r is the gas constant, and T is the temperature. Okay, if I divide that, so it will be dp upon p is equal to minus rho g naught dh upon rho rt. So I get this expression, which is the expression of pressure variation for some particular point, and if I want to get the expression for the entire range of the pressure and for the altitude, so I'll have to integrate it over the ranges of p1 to p for pressure and h1 to h for the altitude. Okay, so if I do that, what I get on the right hand side, I get natural log of p upon p1. On the left hand side I get minus g naught upon rt h minus h1. okay, which also can be written as e power minus g naught upon rt h minus h1. Okay, but in question it is the density variation which is asked. So I know that p upon p1 is what, using the equation of state, rho r t upon rho 1 r t1. T and t1 is same, r is constant, density is variable, so rho by rho 1 is basically equal to p by p1. That means it is also equal to rho by rho 1, and our answer A is correct. Okay, now next question is question number 7. So in question number 7, if we read, for constant free stream velocity and density, a change in lift for a large aspect ratio straight wing within thin cambered airfoil section at small angles of attack leads to, option A is a shift of the aerodynamic center and no shift of the center of pressure. So if you know what is aerodynamic center and center of pressure, you can easily eliminate this option, because shift of aerodynamic center is never there, because aerodynamic center is a constant location, generally 0.25 for subsonic airfoil and zero point 0.5 for supersonic airfoils, whereas center of pressure basically travels with respect to alpha, and here in this it is no shift, so this option is incorrect. Second option is a shift of the center of pressure and no shift of the aerodynamic center, so this seems correct. But before that we should review option C and D as well. So shift of both the aerodynamic center and the center of pressure, uh, it's not possible. No shift either of the aerodynamic center and of the center of pressure, so this is also an irrelevant answer here, so correct answer is option B. Okay, next is question number 8. Which one of the following modes of a stable aircraft has non-oscillatory response characteristics? Okay, so if you know what is short period, phugoid and Dutch roll, then easily you can say these are all the oscillatory response characteristics. We can discuss one by one. So short period is basically, let's say this is the initial flight path of the airplane, and it, because of some disturbances, sudden disturbances, now it is at this location, and when it is a statically stable case, then it will try to come back like this. Okay, and if it behaves in this particular manner, so it takes very short time to come back to its initial position, so that is why it is called short period mode. Okay, and since airplane is crossing its initial position over the period of time, so that is why it is an oscillatory motion. Second is phugoid mode. So in phugoid mode what happens, generally it is also known as long period mode. So long period means disturbances are there, then airplane takes time to come back to its initial position like this. Okay, so it is basically underdamped. This is underdamped, we can say this is overdamped, or highly damped we can say. When next is Dutch roll. Dutch roll is what? Dutch roll is basically the combination of yaw and the roll motion. So let's say if I am the observer and airplane is coming from that direction, this is the front view of the airplane. So if this is the flight path down the line, so if there is no oscillation, so it should follow this straight line. Otherwise, if it is a Dutch roll, airplane will behave in this manner, like this, like this, like this. So it will be moving like this. That means it is crossing its path again and again. That means it is a sign of oscillatory motion. So this is also not correct. So these three are wrong answer, and the correct answer is spiral. And what happens in a spiral? The aircraft keeps losing its altitude and it never goes back to its initial position. That is why it never crosses this line. So this is a non-oscillatory response characteristics of an airplane, stable airplane. Next question is question number 9. A candidate for a vertical tail which one of the following sections is appropriate? So if you know little about vertical tail design, so obviously you should know that answer is this, because this is the example of an symmetric airfoil, others are cambered airfoil. Okay, and why symmetric airfoil is required? Because let's say in its trimmed position, when the elevator is, when the tail is vertical tail is at its zero angle, so in that case there should not be any side force. Okay, and that is only possible in case of symmetric airfoil. If I deflect the angle in this side by 3 degree or in this side by 3 degree, though in both the cases there should be a change in lift by the with the equal magnitude, and that is only possible when I use the symmetric airfoil. That is why answer A is correct. Then primary purpose of a trailing edge flap. Very simple question. To increase the CL max, because a flap is basically a high lift device. If you look at the diagram here, it is something like this. Let's say this is the flap. Okay, so because of flap, what is visible here, that it increases its surface area as well as the camber. Okay, and camber is increased, so obviously there is an increment in CL max values. Okay, this is CL max, let's say for without flap, and this is for flap, so it will be the higher value. That is why increase CL max is the correct option here. Now next is an aircraft in level and unaccelerated flight with a velocity of 300 meters per second require power of this much, and the aircraft weighs this much. The left to drag ratio is okay. So we know that power is thrust into velocity. Okay, so thrust will be power by velocity, or 9 into 10 to the power 6 watts by 300. So I'll get the velocity from here. This will become 4, this will become 3, so 30,000 newtons. And since it is a level and unaccelerated flight, so thrust is equal to drag, which is this. So I have the value of drag now, and also from level and unaccelerated flight, lift is equal to weight. So I have weight given in the numerical, so lift is also known to me, so easily I can get what is L by D. So 1.5 into 10 to the power 5 upon 30, or let's say this. Okay, so it is 15 by 3. 5 is the answer, lift to drag ratio. So I'll stop this video here. If you like this, please watch my part 2 of this video and share both the parts with your friends who are your colleagues, who are your friends in aerospace engineering and BTech aerospace engineering and preparing for gate also. So for both it is equally useful. So with this I'll say thanks and take care.